I would like to tell you two examples from my research where we leverage organocell chemistry to manipulate copper atoms at both a two-dimensional and a one-dimensional level for advanced electronics. Copper is one of the most important metals on Earth. It is extremely important, not only because of its high conductivity and also its great abundance. And these two unparalleled advantages of copper truly makes the use of copper ubiquitous. You can find copper in microprocessors in any of your smartphones. You can find copper in the powerful electronic devices that are embedded in the self-driving cars that are now on the streets of Silicon Valley. Copper is really widely used in not only existing technology, but emerging technology. In existing technology, copper faces two main challenges of weak adhesion and poor stress and electron migration performance. Copper faces a major weak adhesion problem because of a thin layer of copper oxide that grows immediately and uninhibitedly upon exposure of copper to air. And that oxide is very weak, fundamentally prevents good adhesion occur to copper. The second challenge that copper faces is poor stress and electron migration performance. Stress or electron migration refers to the phenomena where copper atoms migrate under either an external stress gradient or electric field, migrating from locations of high potential energy to low potential energy. These migrating copper atoms will create voids inside copper conducting lines, and eventually leads to open circuits, which corrupt your microelectronic device. One way to address that challenge is by adhering another material strongly to the copper surface, which will effectively fix its surface copper atoms and limiting their mobility. On the right shows the electron migration relationship of voids growth rate inside copper conducting lines as a function of interfacial adhesion on the copper surface. What we see is that the larger the interfacial adhesion towards your right, the lower the voids growth rate inside copper conducting lines. Based on this relationship, we believe that the two challenges that copper faces can be solved in one shot. By depositing a material on the copper surface that not only reduces the weak copper oxide, but to bond strongly with copper. And that becomes the first challenge that we will talk through in the first part of this talk for existing technology. For emerging technology, copper continues to play an essential role. The Moore's law, the yardstick by which chip and system manufacturer gauge progress, posits the number of transistors that can be placed inexpensively on a microelectronic device doubles approximately every 2 years. Historically, the semiconductor manufacturers have been keeping pace by continuously shrinking the feature size to increase the number of transistors on a circuit. That had been fine up to now. But as we get closer and closer towards extremely small feature size that are not measured by the number of the tens or hundreds of nanometers, but are instead measured by the number of atoms in between features, it truly becomes increasingly difficult for semiconductor manufacturers to keep pace. And one way to address that challenge is by growing material from the ground up, one atom at a time. 1 year ago, Dr. Hao from Professor Malash's group reported on a successful synthesis of a one-dimensional electric conducting nanowire that has a conductivity that's comparable to intrinsic silicon, even though those nanowires only have 3 inorganic atoms at the cross section. This is a perfect example of bottom-up synthesis of advanced materials to enable next generation advanced electronics. And after seeing the great promise of that technology, we wanted to push the capability even further. We wanted to gain more control over the nanowires structure and to synthesize them on larger scale using simpler organosil molecules. So here's an outline of what we're going to talk about. In the first part of this talk, I'll show an example from my research where we leverage organosil chemistry to reduce the copper oxide on the copper surface and improving the interfacial adhesion at the weak two-dimensional copper surface for existing technology. And then in the second part of this talk, I will give another example from my research that again leverage organosil chemistry to grow one-dimensional electroconducting nanowires for emerging technology. To address the weak copper interface challenge faced in the existing technology, we deposited a hybrid layer on the copper surface. We chose a hybrid layer specifically for its great capability to promote bonding at chemically distinct interfaces, namely an inorganic substrate as shown here and an organic encapsulation material on the top. The reason that this hybrid layer is capable of promoting bonding at a chemically distinct interface is that the hybrid layer itself contains both organic and inorganic components, with functional groups that match the chemistry between the two adjacent interfaces that the hybrid layer is trying to bring together. Additionally, the organic and the inorganic components in the hybrid layer can also form strong chemical bond within itself, ensuring the mechanical stability of the hybrid layer itself, so that when we use the hybrid layer to promote bonding at a chemically distinct interface, itself will not become the weakest interface in the entire test structure. In terms of the composition of our hybrid film, our hybrid film contains an epoxy functionalized silane molecule, GPTMS, which will form the organic part of the hybrid molecular network, and then zirconium alkoxide, which will form the inorganic part of the molecular network. What I want you to pay attention to is this molecule over here, the organosil. We chose this molecule specifically for its sial function, which can not only reduce the copper oxide, but form strong bond with underlying copper surface. Here is a brief summary of the copper oxide reduction and also the formation of strong copper-sulfur bond at the newly exposed copper surface. When the unreacted organosil molecule, MPMS, first come into contact with the copper substrate containing a thin layer of oxide as depicted by Dr. Brown, it first reduces the copper oxide by forming either bisulfite or sulfonated terminated silane molecule, or releasing of water during that process. And that's the copper oxide reduction part of the reaction. In terms of formation of the strong copper-sulfur bond, when the organosil molecule comes into contact with a newly exposed clean copper surface, either the sulfur from unreacted organosil or sulfur from disulfide can react with the salt onto the clean surface. And this will result in a monolayer of organosil on the clean copper surface without pointing methoxy groups. So that's how the chemistry works. Basically, the sial function group can not only reduce the copper oxide, but also form strong bonding with the underlying copper. Let me walk through how we synthesized and deposited our hybrid layer. Our hybrid layer are synthesized through a sol-gel process, whereby we started by dissolving GPTMS and MPTMS in an excess amount of water. And this leads to the start of GPTMS and MPTMS hydrolysis. Then in a second vial, we stabilize the zirconium alkoxide with glycosidic acid to prevent the zirconium alkoxide from quickly precipitating out of solution. We then add the acid stabilized zirconium species to the TBTMS plus MTMS plus water solution to start the sol-gel reaction. And during this time, a series of hydrolysis and condensation reactions occur, whereby the acid stabilized zirconium species becomes more and more soluble in solution over time and react either with other zirconium species to form a zirconium network consisting of zirconium oxygen zirconium bonds, or the zirconium can also react with silane molecules to form the mixed oxide zirconium oxygen silicon bonds. The silane molecules can also react with themselves to form an organosilicon network consisting of silicon oxygen silicon bonds. And then we deep coat our copper substrate into the sol-gel solution and withdraw at a predetermined time. And by doing that, we will achieve a graded hybrid layer that is optimized for bonding the chemically distinct interfaces. The reason that we put down this hybrid layer on the copper surface is to promote adhesion on the copper surface. What kind of adhesion improvement do we get by putting down this hybrid layer? The first data point is a measure of adhesion at copper epoxy interface without the presence of any hybrid layer. Basically, we bond together two plain copper substrates, as shown in orange, using brittle epoxy as shown in yellow. And then we break it apart and measure adhesion. And then the adhesion energy measure for that case is very low, of only 10 joules per meter squared. And fracture paths, as indicated by the red arrow, occurred right in between the yellow epoxy and orange copper beam, where the copper oxide is. And that's actually expected, because failure will always occur at the weakest interface, which is the copper oxide layer in our structure. And if we now apply our hybrid film but contained no or a very little amount of organosiol that we had been talking about, we see a similar fracture energy of only 10 joules per meter squared. And the failure still occur near the copper surface in between the hybrid layer and the copper beam, which is again within the weak copper oxide layer. Now, what would happen when we incorporate the organosiol into our hybrid layer composition? This is what happened. When we added the organosiol to the hybrid layer composition, we saw a marked increase in adhesion energy to a maximum of 90 joules per meter squared. And more surprisingly, the fracture path changed from the hybrid layer copper interface to within a very strong brittle epoxy. And that's an indication of a much strengthened hybrid layer copper interface and possible removal of copper oxide. Because if copper oxide is still there, the adhesion will still be very low. And the adhesion energy will only be around 10 joules per meter squared. Now that we have achieved high performance copper adhesion, the next question we wondered was whether we have indeed reduced the copper oxide. This is only circumstantial evidence. We want some more direct evidence. And to quantify that, we performed transmission electron microscopy, looking right at the hybrid layer copper interface where the copper oxide should exist. Here shows atomic TEM images of the hybrid layer copper interface containing no organosiol. And what we see is the existence of a copper oxide layer of about 2 nanometers thickness that uniformly covers the entire copper surface. And that oxide layer is determined to be cupric oxide, as the 2.47 angstrom lattice spacing matched perfectly with the 2.47 angstrom spacing reported in literature for cupric oxide measured by XRD measurements. In addition to confirm the accuracy of our measurements, we also measured the lattice spacing for bulk copper, and that turned out to be 2.13 angstrom, which again matched nicely with the 2.09 for bulk copper. So this is for a case where the hybrid layer is deposited on copper containing no organosil, where we still see the presence of copper oxide. What would be a case where the hybrid layer contains organosil? Well, we still see the copper oxide that's on the surface. This is what happened. With 10% inclusion of organosil into the hybrid layer, the copper oxide is absent. And that's evidenced by the measured lattice spacing of 2.10 for the surface of that sample, which matches nicely with the value of bulk copper. So with this, we provided definitive proof to copper oxide reduction with hybrid layer deposit on copper containing organosil. If you remember at the beginning of this talk, we mentioned there are three parts that we want to address. One is the weak copper oxide reduction. The copper oxide reduction, one is forms strong bond with the underlying copper, and the other is improve pore stress and electron migration performance. Now that we have achieved high performance adhesion, achieved copper oxide reduction, we wonder whether the same hybrid layer strategy can bring about a improved copper stress and electron migration performance as well. And to quantify that, we performed copper stress relaxation experiment. Basically, we introduced compressive stress into copper films and see how quickly that compressive copper stress relaxes over time. The quicker and the more severe the stress relaxation is, the worse the stress relaxation performance. Why? Because stress relaxation is achieved by migrating copper atoms to release the internal stress. And the quicker or the more severe the stress relaxation is, the more migrating copper atoms. And more migrating copper atoms means more voids will be created inside copper conducting lines, which will lead to open circuits and damage your device. So we basically want to minimize copper stress relaxation as much as possible. The orange dotted line shows the stress profile for copper film for the ideal case or the hypothetically perfect case, where no copper atom is allowed to move. And what we see is that the copper film stress remains constant during the entire stress relaxation experiment. And this is the type of behavior that we want. We don't want any copper atoms to move because that will degrade our device. So measuring our samples, the black shows the copper film stress relaxation in the absence of any hybrid layer. And then the blue shows the copper stress relaxation for a sample that's passivated with hybrid layer but contains no organosil. And then the red shows our copper film passivated with hybrid layer containing organosil. And what we immediately see is that the copper film passivated with our hybrid layer containing organosil, as shown in red, has the best performance in terms of both a slower stress relaxation at the beginning of the experiment and a larger residual stress at the end of the experiment. So this shows that our hybrid layer is very effective in passivating copper film experiencing compression, as indicated by the negative sign in front of the stress. We've also wondered whether our hybrid layer will be effective for passivating copper films when copper film is under tension. In fact, we do. Our hybrid layer passivated copper surface also has the best performance in terms of a higher residual stress at the end of the stress relaxation experiment. And in fact, similar stress relaxation profile have been reported in literature. To summarize, in the first part of this talk, I showed you one example from my research that leveraged organothiochemistry to reduce the copper oxide and to address it to a weak copper oxide interface problem faced by existing technology. And to address that, we developed a hybrid layer deposition strategy. And with that strategy, we demonstrate a successful reduction of copper oxide, improved bonding at the copper surface, and a suppressed copper, or improves copper migration performance. And we further prove that this improved stress relaxation performance is stress state insensitive, meaning that our hybrid layer is as effective in passivating copper film under compression as under tension. So that's our work focusing on existing technology. And in emerging technology, copper continues to be an essential component to microprocessor design and evolution. And now I want to give you another example from my research, where we focused on leveraging organothiochemistry to grow one-dimensional electrically conducting nanowires for emerging technology. To grow these electrically conducting nanowires, we use two benzene thiol molecules, as shown on the left. The 4-aminothiophenol, or 4-ATP, and 3,5-dimethylbenzene thiol, or 3,5-DBT. And we grow our material using two different methods. One is the substrate method on top, and one is the solution synthesis shown on the bottom. In terms of the substrate method, we first dissolve our benzene thiol in ethanol solution to prepare a low concentration organothiol solution. We then submerge a copper film into that solution. Let the benzene thiol, either 4-ATP or 3,5-DBT, to react with the copper. And then we call the end result either 4-ATP copper or 3,5-DBT copper. And the second route we took is solution synthesis, whereby we start by dissolving copper sulfate in ethylene glycol to obtain some copper ions, and then we add to that first solution an ethylene glycol dissolved benzene thiol solution to let the benzene thiol to react with copper, and again to form the same product, 4-ATP copper or 3,5-DBT copper. And that's how we synthesized our nanowires. Here shows scanning electron microscopy images of the products that we formed. On the left is the 4-ATP copper product formed by the solution method, or substrate method. And on the right are two images showing the products formed by the solution synthesis. To give you a preview of what we are looking at, you are looking at the macroscopic shapes of tightly bundled microscopic nanowires. Or in other words, many of the extremely thin nanowires are tightly bundled to form the macroscopic shapes you are seeing under SEM. I will prove this just a little later. And in terms of the morphology for each benzene thiol molecule that we have used, the 4-ATP copper, regardless of how 4-ATP copper is synthesized, whether it's substrate grown or solution synthesized, its structure always had a lot of branches. And in contrast, the morphology that's formed by 3,5-DBT copper are all very straight, raw-like material. Keep this morphology in mind as we will refer back to it later on as we look at other results. Now we know the morphology of our nanowires. What about their chemical composition? To determine the chemical composition of our materials, we conducted X-ray photoelectron spectroscopy. Here shows XPS spectrum of our materials that's being synthesized. This is for 4-ATP copper, and know that similar spectrum have been obtained for 3,5-DBT copper as well. And I want you to know this approximately 1-to-1 copper-sulfur ratio in this material. This ratio is very important as it tells us, on average, when the 4-ATP and copper react, or 3,5-DBT and copper react, one 4-ATP copper will bind with one copper atom. It is also interesting to note that identical ratios have been obtained for regardless of the synthetic method, whether it's substrate grown or whether it's solution synthesized. Meaning that the synthetic process don't affect the process the chemical composition of the material that's get formed. Note also the absence of a copper satellite peak in between the two peaks, indicating of the copper in the 1+ charge state. Because if it's copper 2+, then there will be a small bump in between the two more dominant peaks. And this copper 1+ charge state is actually expected because when the sulfur from when the 4-ATP or 3,5-DBT deprotonate, it will have a sulfur 1-. And then when the copper ion binds to it, it has to be copper 1+ if we want to maintain charge neutrality. Copper 1-, sulfur 1-, and copper 1+. Now we know the morphology of our material and we know their chemical compositions. We also wondered about the structure of these materials, whether they are highly crystalline or whether they are completely amorphous. And to test for that, we conducted X-ray X-ray diffraction. Here's the X-ray spectra of our materials. 3,5-DBT copper shown in blue and 4-ATP copper shown in red. What we immediately see are the two dominant peaks at very low diffraction angles, which corresponds to very large d spacings in our material, or very large spacings that periodically appear in our material. And note also there are some smaller subsidiary peaks towards larger diffraction angles corresponding to smaller d spacings, and we will get back to this XRT spectra later and relate it to our proposed spectrum, a proposed molecular structure. To understand the exact structure of our material, we sought help from our former group member, Joe Berg, to provide some molecular dynamic simulations. Basically, we started by putting into empty simulation cells the precursors that we needed. The copper 1+ ion, as determined from XPS spectra earlier, and either deprotonated 4-ATP or 3,5-DBT molecules. We then let the randomly positioned molecular precursors to start self-assembly and see what kind of structure molecular dynamic simulation result or molecular dynamic simulation will predict. And at the end of the simulation, here are the structures that were outputted. On the left is the predicted 4-ATP copper structure, and on the right are the 3,5-DBT copper structure. What we see are that nanowires readily form for both material systems, whether it's 4-ATP copper or 3,5-DBT copper. And what's even more surprising was the fact that these nanowires that form are core shell nanowires. And that's indicated by the yellow sulfur and orange copper atoms that are located in the middle of those nanowires, with darker gray benzene carbon atoms from the aromatic ring surrounding it on the outside. Note also the branching morphology for the 4-ATP copper, which is absent in the 3,5-DBT copper, where only straight nanowires have been formed. And this result is actually consistent with our SEM from earlier, in that 4-ATP copper nanowires had a lot of branches, and that's a result of the branched microstructure of 4-ATP nanowire. And the straight rod-like 3,5-DBT copper nanowires are the result of very straight individual 3,5-DBT nanowires. So those two results relate up very well. Because what we really want at this point is a precise account of the atomic structure inside our nanowires. We went one step further and perform density functional relaxations on the nanowire structures that we have been obtained from molecular dynamic simulation. And Yao from the Evans group helped us on that. And so after all the atoms are eventually happy with their locations, after the total system energy has been minimized, this is the structure that we have obtained. What we see is an atomically well-defined core shell structure with an inorganic core and an organic shell. And looking at the core of this material, what we see is that within each cross-section, within each layer, it contains either 5 copper atoms or 5 sulfur atoms. And those layers are arranged in an alternating fashion. And though each copper atom binds to 3 sulfur atoms in a distorted trigonoplanar geometry, and each sulfur atom, in addition to binding with its own aromatic ring, binds with 3 copper atoms in a distorted tetrahedral geometry. And on the right shows the top-down view of the 2-layer structure that we have been using for the DFT relaxation, with the darker gray of the aromatic ring coloring darker gray being actually on the 2nd level. So what that image tells us is that the aromatic rings inside the nanowire don't stack directly on top of each other, but are instead arranged in a staggered geometry. And in fact, similar structure have been obtained for 3,5-DBT copper as well. Now, at this point, what we really want is a glimpse into, and now let's relate it back to the XRD spectrum from earlier. Remember that the 2 dominant peaks corresponding to very large spacings, that periodically appear on material, of 14.3 angstrom for the 3,5-DBT copper and 16.4 for the 4-ATP copper. These 2 numbers actually correlate very well with our predicted diameter of our nanowires. The 19.3 angstrom for 3,5-DBT copper matches nicely with the 14.3 angstrom as recorded in XRD, and then the 16.6 angstrom for the 4-ATP nanowire, again, corresponding very nicely with the 14.4 angstrom from XRD. So what's happening here is that many of the extremely thin 16 nanometer angstrom diameter nanowires are tightly bundled together to form our material in the nanowire's radial direction. And that tight bundling gives substantial presence of periodicity along the nanowire's radial direction in terms of nanowire's diameters. And that leads to this to the peak being detected by XRD and show up as very intense peaks. Some of you might have also noticed that the most dominant peak for 3,5-DBT copper is much more intense than for 4-ATP copper. And the reason for that is actually quite simple. When the 3,5-DBT individual nanowires pack, they pack much better. They align in a much more uniform way. Remember that the 3,5-DBT copper nanowires are all very straight. And straight nanowires makes alignment easy, whereas 4-ATP copper nanowires had a lot of branching. Branching makes alignment difficult. And better alignment means better packing. Better packing means better periodicity, and better periodicity means stronger XRD signal. And at this point, what we really want is a glimpse into the atomic structure of our nanowires using some type of experimental technique. And what's a better way to do this other than the use of a transmission electron microscope? So we collected transmission TEM images of the 4-ATP copper core shell nanowire. What we see if the identical branching out feature, as we had observed from XRD and MD simulation for this 4TP copper nanowire from earlier. And if we zoom into one of the seemingly amorphous regions, what we see are intriguing patterns that look exactly like the core shell structure that we had been seeing, with a core in the middle and a shell on the peripheral. And because this is the 4HP copper material that we are examining, if these cylindrical shapes on the side are indeed the 4HP molecules, then we can measure their pi-pi stack distance to be 3.7 angstrom approximately. And that matched very nicely with the little reported value of 3.5 for pi-pi stacked aromatic rings. And if we measure the length of those cylindrical shapes, which presumably to be our 4ATP molecules, the length again matched very nicely with the length of individual 4ATP 4ATP molecule. So there are two things that this set of TM image tells us. First is that we indeed get core shell nanowires. And second, many of these nanowires are indeed tightly bundled together to form the macroscopic shapes that we are seeing either low magnification TEM or from SEM. The last and perhaps the most mysterious aspect of our material is whether it is conductive. And to quantify that, we sought help from Dr. Hao from Professor Malosha's group and conducted electrochemical impedance spectroscopy. Impedance is, in simple terms, the resistance of a material to current flow. And impedance is different from resistance that everyone is familiar with, in that the impedance incorporates an additional phase term, the phase difference between the applied voltage and the resulting current. And we collected the impedance spectroscopy by applying a sinusoidal voltage on our nanowire powder specimen sandwiched in between two electrochemical plates, and then measure the resulting current. And then by plotting both the real and the imaginary parts of the impedance, we obtain these Nyquist plots. Red and blue data dots show our collected impedance result for 4ATP copper and 3,5 DBT copper respectively. And black line shows the computer-generated least square fitting to our experimental result. And using this equivalent circuit as shown here, the equivalent circuit contains two parts. The first part is a capacitor in parallel with a resistor, which will give the device semicircle shape as shown here, and then a constant phase element in parallel with a resistor, which will give the shape of the long straight pair towards your right. So indeed, very good fit has been obtained using this equivalent circuit model. And the reason that we use this equivalent circuit model is because we wanted to extract the resistance of both our inorganic core and the organic shell of our material. And in fact, the electronic transport inside the inorganic core will be modeled by the first part of the equivalent circuit, and that of the organic shell will be modeled by the second. And here is a visual representation of what each equivalent circuit element represents. So using this equivalent circuit model and extracting out extrinsic resistance of our material, both the inorganic core and the organic shell, we then converted the extrinsic resistance to intrinsic resistivity, which then does not depend on the shape of our material. And the intrinsic resistivity of both the organic shell and inorganic core are tabulated here. The resistivity of the organic shell for 3,5 DBT copper is on the order of 10 to the 20 ohm meter, and on the order of 10 to the 19 for 4ATP copper. And the resistivity for the inorganic core for 3,5 DBT copper is on the order of 10 to the 6, and is on the order of 10 to the 5th for 4ATP copper. Note, however, these numbers cannot be compared directly with the resistivity of other material, because both the grain size and their orientation profoundly change the measured resistance. And note that our nanowire, when we measure it, is completely randomly oriented in between our electrochemical plates. And with many nanowires that are parallel to the plates, which will have absolutely no use in conducting electricity across. And therefore, this will result in a measured resistance for our nanowires to be orders of magnitude higher than if we measure directly from the two ends of a highly aligned nanowire array. And in fact, Dr. Hao's work comparing the resistance difference between the two systems, he has found that the resistance measured by measuring directly from the two ends of a highly aligned nanowire array is 3 orders of magnitude lower than that measured on a complete randomly oriented nanowire powder, as in our case. So if that's true, and with a similar 3 orders of magnitude reduction in resistivity, that will put the resistivity of our best performing 4ADP covered nanowires to be even better than intrinsic silicon. To summarize, in the second part of this talk, I showed again how we leverage organothiochemistry to address for emerging technology. And we demonstrate the successful synthesis of a new class of core shell nanowire using bending style. And the atomic arrangement inside these nanowires were unraveled using computational methods and atomic resolution TM imaging. And we show that these nanowires contain only 5 inorganic atoms at the cross section. Furthermore, we proved the electrically conducting nature of these nanowires, which might even outperform intrinsic silicon. So putting all this in one sentence, I just gave a quick demonstration of organothio's capability to direct inorganic bonding of copper atoms for both existing and emerging technologies. Too many people have helped, and a few have even sacrificed for me to come to this point. And I want to start off by thanking Professor Dauskardt. Thank you, Professor, for your generous offer for me to join this fabulous group that marks the beginning of my PhD career. Thank you for your support when I wanted to learn some of the more expensive techniques. And thank you for setting up green models for us to learn from in terms of how to write and how to give presentations. Thank you. And next, I want to thank Professor Saleo, my committee members, starting from Professor Saleo. I want to thank Professor Saleo for being there every step of my way here at Stanford, starting from 204 to my qualifying exam and to now to my reading and defense committee. It really means a lot to me. Thank you. And I want next thank Professor Maloche for being on both my reading and committee and my defense committee. And thank Professor Gu for chairing it and Professor Prince for serving on it. Thank you all for your support, guidance, and feedback on my research. And people often at Stanford often say that those you learn the most from aren't necessarily your professors, but your extraordinary peers. I didn't fully recognize this until my 4th year, when one day suddenly reflecting upon all the personal changes I've made since starting school at Stanford. And for that, I truly want to thank all my extraordinary peers in the Dauskardt group. Thank you all for setting up so many exemplary models that I can constantly learn from. And next, I want to thank the research scientists that I have interacted and collaborated here from Stanford and from IBM. and Marshall especially. Thank you all for the knowledge that you passed down to me and for all the fruitful discussions on my research. I'm sure my research wouldn't have gone so smoothly without you. Next, I want to thank the staff members at the Department of Material Science and Engineering for always being so helpful. And next, I want to acknowledge my undergraduate research advisors for their guidance and support when I was at RPI. Their exceptional tutelage have truly paved my way into coming to Stanford. Next up, my friends. Friends that I made here at Stanford and friends from undergrad and high school. Your presence in my life constantly brings me warmth and it reminds me the value of our long-lasting friendships. Thank you all for your presence in my life. You made this PhD journey much more enjoyable. Next, I want to thank my family. I want to thank, and this includes my grandparents, my 3 cousins, my host family from Connecticut, and my Uncle Jim's family, and my parents-in-law. I want to thank them all for the constant and tremendous love and support they have given me, which makes me a warm and caring person. And next, I want to thank my parents. It was my father who paid extreme attention to all my weaknesses and made sure to go whatever long way necessary to correct them, even if it meant for him to be temporarily hit by his unenlightened son. And it was my mother, a woman who wasn't willing to buy expensive clothes and fashionable clothing, but instead saved it all up and spent it, and never thought twice about spending it all on my extremely expensive college education. And I want to thank them all for their unconditional love and support. And I'll make sure that I'll use the rest of my life to pay back and forward. Last but not least, I want to thank my wife, Yao. Marrying Yao has opened up an entire new chapter in my life. It was Yao's confidence in herself as well as in me that led to me gaining confidence. And it was Yao's lovely giggles and silly dances at home that lightened my mood after some long and difficult days in the lab. Thank you. A big thank you to all of you whose presence in my life made this moment possible. Thank you.
Have you checked if turbo treatment such as annealing changes the morphology of those wires?
So you're asking whether we have tried to use different temperature to synthesize,
or maybe
structures, different
like
structures.
annealing, whether annealing changes.
We haven't. Yes.
I wonder if you could zoom out on your, so you showed that really high resolution picture of the wires, and if you could do diffraction on those samples, if you've got enough there, or even if you could see the same spacings using PM as you could see in the X-rays.
The spacing we measured for the stacking for 40P matched nicely with reported literature results from literature. And also it matches with the peaks from XRD as well, as you mentioned.
Mm-hmm.
In fact, if you look at this broad peak over here, in between 3.2 and 3.9, that's exactly the Parhite stack distance between aromatic rings.
we in fact do have a correlation between XRD as well as from the our TEM image shown here.
Right, I just think it would also should be easy to take either electron diffraction if they're stable enough, or FFTs of maybe perhaps zoomed out images, and also show a more sort of in between the X-rays and that very high resolution picture.
Yeah, I think that's.
We should try.
Yes, we should try. Yes.
Yeah, and then in the XRD, what were the other high, the large stations, the 9.2 and the 8.1?
It's 9.2 we are still trying to figure out, but I think it's somehow related to the branching feature of 480p, because it's kind of only shown up for 480p. So the 480p, because of 480p has a lot of branches, the structure is very difficult to hack, and therefore that decreases the most dominant peak and then increases subsidiary peak. And on the other hand, for the 35dp copper, the most dominant peak is very high, and therefore, and we don't see that subsidiary peak. So we think that's related to the branching feature of the structure. But exactly in terms of what it is, we're still trying to figure out. Yes.
With the hybrid layers containing organothiol, do you think that, well, one, is electromigration an issue outside of the interface? And do you expect it to just mitigate electromigration that occurs at the interface as opposed to inside the bulk of the copper?
Yeah, for this hybrid layer strategy that we developed, we are aiming to mitigate the surface copper atom migration. Hybrid film don't go into the copper contaminate themselves. Right. So that's the surface copper migration that we are trying to minimize.
Good. Okay. Well, thank you. This concludes the open session of this session.